Hello students, and once again welcome back to the Chem School. Now today we are going to talk about a very important topic in inorganic chemistry, and that is coordination complexes. Okay, so today's lecture we will try to understand what is a coordination complex and how do we draw or how do we write down a coordination complex. Okay, so let's get started. So basically we are going to talk about the structure and not the IUPAC nomenclature. Okay, so now what are the conditions for making a coordination complex? Okay, so the first condition is that they should have an empty orbital. Okay, and usually it is with respect to the d orbital. So they should have an empty d orbitals. So if you have an empty d orbital, okay, it means you're talking about the metals, because d orbital is with respect to the transition metals. Okay, so if you have an empty d orbital, it means these are transition metals. So transition metals can form coordination complexes. There are other exceptions also, that is from p block. Aluminum can also form coordination complex. Why? Because the same reason, it has empty d orbital. Okay, fine. So the first most important criteria is you should have an empty d orbital. Okay, now when we have an empty d orbital, what happens? Okay, let's say in general the metal we will write down as M. Okay, so metal, now just imagine, okay, that you have iron, and if you keep an iron, okay, which is close to a magnet, so what will happen? Okay, all the iron particles will get attracted towards the magnet, right? It is the same thing. If you have a solution and you have a transition metal, so in that transition metal, in that particular solution, the metal will be selective to some ions. Okay, and it will attract that ions on its surface, forming some different types of bond. Now let's understand what I meant to say in detail. So let's assume this was the metal, okay, and we have kept it in a solution, and this metal is now attracting some ions. Okay, that particular ions we will give a special name which is called as ligands. I repeat, your L is nothing but a ligand. So L is called as ligands, and ligands are nothing but, you can say, ions, or they can be neutral species. Okay, what is the main logic? Okay, so this ligands will get attracted on the surface of the metal at different sites. Okay, and then they form a special type of bond that is called as coordinate bond. Okay, now we know that in coordinate bond what will happen? The ligand is going to be the donor. Okay, the ligand is nothing but an electron donor. So both the bond formation electrons will come from the ligand. Okay, and that is what is meant by a coordinate bond, when one species donate both the electron for bond formation. So here this ligand will keep its electron where? In the empty d orbital. So that is the reason you should have an empty d orbital. So this ligand will keep the electron in the empty d orbital of this metal. Okay, and therefore this bond is your coordinate bond. So you have different coordinate bond that is getting formed. Okay, and the number of coordinate bond that is formed across this metal, okay, is called as ligancy. Okay, I repeat, number of coordinate bond is equal to ligancy, or you can say it is the coordination number. Is this clear? Fine. So across this metal, you can see you have 1, 2, 3, 4, 5, 6 coordinate bond. It means the coordination number of this metal is going to be 6. Okay, or the ligancy is going to be 6. Is this clear? Now the next thing, the species that you have immediately next to the metals, okay, you can just draw them in dotted circle. And let's say that this is a sphere, okay, because it is going to be a 3-dimensional structure. Okay, so the ligands will be attached, okay, on all the sides of the metal. So it is going to be a 3-dimensional structure. So we call it as a sphere. So the first sphere of ligands across the metal, this is called as the coordination sphere. I repeat, this is called as the coordination sphere. And this is important. Why? Because this coordination sphere will decide the geometry of the metal. I repeat, this ligands, the method, the way by which the ligand is attached to the metal, they will decide the geometry of the complex. Is this clear? So ligands decide the geometry of the complex, or the coordination sphere will decide the ligands will decide the geometry of the complex. Let's make it simple. Okay. Now, apart from this, see, the metal is a cation, right? I repeat, the metal is a cation. So it can attract different ions on its surface, right? So it can attract positive ions as well as the negative ion. Okay, why? Suppose this is a cation. Okay, it can attract an ion. The other thing, the ligand can be an anion, so it can attract a cation. Okay, and vice versa. That is the reason, if this is anionic, you can have cation attached on its surface. Okay, if this is metal, has to be cationic, so it will attach an ion on its surface. That is the reason across the coordination sphere you can have one more sphere, and that will draw in solid line. Okay, so the dotted line sphere is the coordination sphere. If I draw something in solid line, okay, so this is called as the primary valence. We can give different names to all of them. Okay, so coordination sphere, with respect to this, if this is the primary valence, then this is going to be the secondary valence. Okay, so the coordination sphere is also called as secondary valence. It has other name which is called as auxiliary valence. So the coordination sphere can also be called as auxiliary valence. The primary valence can also be called as ionization sphere. Why ionization sphere? Because most of time, if you see, the primary valence will decide the oxidation number of the metal. I repeat, the primary valence decide the oxidation number of the metal. That is the reason it is called as the ionization sphere. While the secondary valence will decide the coordination number and the geometry. Okay, I repeat, the secondary valence will decide the coordination number, and therefore it is called as a coordination sphere, and it will also decide the geometry, as we said previously. Okay, so remember metal, then in dotted line what you have drawn, the dotted sphere, that is going to be the coordination sphere. The solid sphere, that is going to be your primary valence or the ionization sphere. So usually this is how you will have your complex, which looks like. Okay, now let's write down some ions in here. So I'll write down, let's say, Cl minus. Okay, so this is how your complex will look like. Okay, fine. Now if you want to write down this in, like, short, so how do we write down? So you will always write down the coordination sphere in square brackets. Okay, I repeat, you will always write down this coordination sphere in square bracket. Okay, usually if you have any, I'll just tell you something more. If you have any cations, so I'm just adding it at this moment. Let's say you have Na plus. It is just an assumption. Okay, so you have 1, 2, 3 Na plus. Okay, so all the cations of the primary valence will come first. The cations of the primary valence will come first. So the cation is Na. How many Na do we have? We have 3 Na. Followed by the coordination sphere. So coordination sphere in square bracket. Okay, in square bracket you will first write down the metal. So the metal, which is M, followed by the ligands. So ligands, how many we have? We have 6. Followed by the anion of the primary valence. So the anion is Cl minus. How many we have? 3. Okay, so outside the square bracket you will have the primary valence. Inside the square bracket you will have the coordination sphere. Okay, then again remember that when you write down outside the square bracket, Okay, first you will write down primary valence cation, then the coordination sphere, in that transition metal followed by the ligands, and then primary valence anion. Okay, so if you don't want to draw this structure, this is how you do the representation, the structural representation of the coordination complex. Okay, so I hope this is very clear. I repeat the sequence. When you do the structural representation, it has to be primary valence cation, followed by in square bracket the transition metal, the ligands, and after closing the square bracket you will take the transition metal anions. Okay, so this today what we have done, this you can also call as Werner's theory. I repeat, this you can also call as Werner's theory. Okay, so he was the one who proposed the coordination complex first, or who introduced this branch. Okay, so he was the one who introduced this branch, and therefore we call this as Werner's theory of coordination compound, and he is known as the father of coordination compound. Is that clear? Fine. So we will talk about this chapter more in detail in the next class. See you soon. Thank you.